Hey there, science fans! Welcome back to another exciting episode where we explore the wonders of engineering. Today, we're diving deep into the fascinating world of synchronous motors, a marvel of modern technology. Picture this, an electric motor that hums along at a constant speed, perfectly in sync with the power supply. No matter the load, it maintains its speed. That's our star of the show, the synchronous motor, a true workhorse in the industrial world. A synchronous motor is a fascinating piece of engineering, meticulously designed to perform with high efficiency and reliability. It's all about precision and timing. Every component is crafted to ensure the motor runs smoothly and accurately. Unlike some motors that can have slight variations in speed, the synchronous motor marches to the beat of its own drum, or rather the frequency of the AC power supply. This consistency is crucial for many applications. This synchronization is key to understanding how these motors work. It ensures that the motor operates efficiently and effectively. The rotor, the spinning part inside, follows the rotating magnetic field generated by the stator, the stationary outer part. This interaction is what makes the motor so unique. It's like a dance, with the rotor and stator moving together in perfect harmony. This precise coordination is what allows the synchronous motor to perform its tasks with such remarkable accuracy and dependability. Now, let's talk about the power source that makes this synchronized dance possible. Three-phase AC power. This type of electricity is like the rhythm section of our motor's band, providing the energy in a specific pattern. Imagine three waves, each slightly offset from the others. That's what three-phase AC power looks like. As these waves interact, they create a rotating magnetic field within the stator of the synchronous motor. This rotating magnetic field is what makes the rotor spin. Think of it like the magnetic poles attracting and repelling each other, causing the rotor to follow along. The speed of this rotation is directly related to the frequency of the AC power supply. Here's the catch with synchronous motors. They're not self-starting. Unlike some motors that can just take off on their own, synchronous motors need a little push to get going. Remember how the rotor needs to be synchronized with the rotating magnetic field? Well, it can't just jump into sync from a standstill. It's like trying to hop onto a moving carousel. You need to match its speed first. That's where external prime movers come in. These are essentially other motors or engines that provide the initial spin to get the synchronous motor up to speed. Once the rotor is close to the synchronous speed, it can lock onto the rotating magnetic field and run smoothly. Section 4. Steady as she goes, constant speed operation. One of the coolest things about synchronous motors is their rock-solid speed control. Once they're up and running, their speed stays constant regardless of the load. Think of it like a cruise control system. Whether the motor is driving a light load or a heavy one, its speed stays locked in. This makes them ideal for applications where precise speed is critical. This constant speed is due to the synchronous nature of the motor. The rotor is constantly trying to keep up with the rotating magnetic field. Even if the load tries to slow it down, the magnetic pull keeps it in sync. Section 5. Power factor control, a balancing act. Power factor is a measure of how effectively electrical power is used. It is a crucial aspect in the management of electrical systems, especially in large-scale industrial operations. A good power factor means efficient energy use, which translates to cost savings. This efficiency is not just about saving money, but also about reducing energy waste and improving the overall performance of electrical systems. Synchronous motors have a neat trick up their sleeve. They can operate at both lagging and leading power factor. This dual capability allows them to be highly versatile in various applications. What does that even mean? It can be a bit confusing at first, but let's break it down. Well, imagine electricity as a flowing river. The flow of electricity can be smooth or obstructed, much like water in a river. Lagging power factor is like a dam restricting the flow, causing inefficiencies and potential energy losses. While leading power factor is like adding a channel to improve it, allowing for a more efficient and effective flow of electricity. By adjusting the field excitation of the synchronous motor, we can control its power factor. This adjustment is key to optimizing the motor's performance and the overall efficiency of the electrical system. This ability makes them valuable in industrial settings where they can be used to improve the overall power factor of the system. By enhancing the power factor, industries can achieve better energy management, reduce costs, and contribute to a more sustainable future. Section 6. Torque comparison, synchronous versus induction motors. Now let's talk about torque. Torque is a measure of rotational force, or how strong a motor is in terms of power. When it comes to starting torque, induction motors have the upper hand. They can generate high starting torque without any special arrangements or modifications. Synchronous motors, on the other hand, have a lower starting torque. Remember, they need that prime mover to get going initially. However, once they reach synchronous speed, their torque is constant and doesn't fluctuate with load changes, so it's a trade-off. Induction motors are great for applications requiring high starting torque, while synchronous motors excel in constant speed, high-efficiency applications. Section 7. Advantages and applications of synchronous motors. Synchronous motors may not be the right choice for every application, but they shine in specific areas where their unique characteristics are highly beneficial. Their constant speed operation makes them ideal for applications requiring precise timing and control, ensuring that processes run smoothly without any interruptions. Think of large industrial processes, power plants, and even some types of clocks. These are environments where precision is not just preferred, but absolutely essential. In these scenarios, a slight variation in motor speed could be disastrous, leading to significant operational issues and potential downtime. Moreover, their ability to operate at a leading power factor makes them valuable for improving overall system efficiency. This characteristic helps in maintaining the stability of the electrical grid. By correcting power factor, they can reduce energy waste and lower electricity costs, making them an economically sound choice for many industries. So next time you see a large piece of machinery humming along at a perfectly constant speed, remember the synchronous motor, a marvel of engineering that keeps our world running smoothly and efficiently. Their role in modern industry is indispensable, ensuring reliability and performance in critical applications.